Hello and welcome to our discussion today about verifying trigonometric identities. If you are using the Blitzer algebra and trigonometry text, you'll find this information in section 6.1. And there's really only one task that we are looking for in this skill, and that is how do we use fundamental trig identities to verify other trigonometric identities. So you probably are wondering what makes a trig identity a fundamental trig identity. And so we're going to talk about the four different classes of fundamental trig identities. And we're going to start with the reciprocal identities, which you probably know like the back of your hand. Sine of theta is the same as 1 over the cosecant of theta. And cosine of theta is the same as 1 over secant theta. We know tangent of theta is 1 over cotangent of theta. And then cosecant of theta will equal 1 over sine of theta. Secant of theta is the same as 1 over the cosine of theta. And cotangent of theta is equal to 1 over tangent of theta. If you know these very well, then that's going to serve you well in this endeavor. And then if you don't, I would suggest you want to memorize them. The next type of fundamental trig identity is the quotient identities, and there's only two of them. These are the two trig functions that can be written as a ratio of two other trig functions. We know that tangent of theta is the same as sine of theta divided by cosine of theta. And since cotangent of theta is the reciprocal of tangent of theta, we can say that it is equal to the cosine of theta divided by the sine of theta. Again, these need to be memorized. Now, the Pythagorean identities, they all stem from the idea that is really generated by the unit circle or any right triangle, really. We can think about this. This is a unit circle, right? And it has a radius of 1. And then we have this right triangle, this reference right triangle that is formed. And we have x here and y here. And when we have a right triangle, we know that the Pythagorean theorem holds, right? X squared plus y squared will equal r squared, which is 1 squared. Okay, so x squared plus y squared is equal to 1. But we know from our exposure to the unit circle that x is the same as cosine and y is the same as sine. So we can rewrite this as sine squared of theta plus cosine squared of theta is equal to 1. Okay, so that is our big kahuna Pythagorean identity. And then we can think of variations of this by just solving for one of these trig functions. Sine squared of theta would be the same as 1 minus the cosine squared of theta. And cosine squared of theta would equal 1 minus sine squared of theta. So definitely you need to know this one and then know how to get to each of these. Now, if we think about taking that original Pythagorean identity and dividing each term through by sine squared of theta, then what's going to happen with each of these terms? They're going to turn into something different, right? Sine squared of theta divided by sine squared of theta will equal 1. Cosine squared of theta divided by sine squared of theta will be cotangent squared of theta. And 1 divided by sine squared of theta is cosecant squared of theta. Then similarly, on the other hand, if we divide everything through by cosine squared of theta, we get the last of the Pythagorean identities. Sine squared of theta divided by cosine squared of theta will equal tangent squared of theta. Cosine squared of theta over itself is 1. And 1 divided by cosine squared of theta is equal to secant squared of theta. So, similar to our original Pythagorean identity, we can solve for 1 in this case or cotangent squared in this case. And with this one in orange, we could solve for tangent squared of theta or 1 here. So all of these are variations of the Pythagorean identities. And if you know this first one, you can definitely derive them all. Take some time and become familiar with them because we will use them a lot when we are verifying. Next are the even and odd trig identities, and we talked a little bit about this when we discussed even and odd properties from the unit circle. But since we know that the sine function and the tangent function are odd, then we know that f of negative x is the same as negative f of x. So sine of negative theta will equal negative sine of theta. Tangent of negative theta will equal negative tangent of theta. Cosecant of negative theta will equal negative cosecant of theta. And cotangent of negative theta will equal negative cotangent of theta. Now, cosine of theta is an even function. Okay, so an even function will mean that f of negative x is the same as f of x. So in this case, cosine of negative theta will equal cosine of theta, and secant of negative theta will also equal positive secant of theta. So what does it mean to verify an identity? Well, verifying or proving an identity just means that we are going to show that the statement is true. Now, there are two main ways that we can do that. One is we can show that one side of the equation is equal to the other by manipulating just one side of the equation. Okay. And the other way we could do that is we can show that both sides of the equation are equal to something completely different. So the left-hand side is equal to something different and the right-hand side is equal to that same something different. That would mean that they would be equal to each other. Okay, so we can use either one of those methods or either one of those techniques. When we're verifying identities, what tools do we have to work with? Well, verifying identities is a lot like solving a mystery. You want to look for clues and then use the appropriate tools to figure out that mystery. So what clues might we look for? Well, we may look for squared trig functions, kind of like sine squared of x or tangent squared of x. If you see squared trig functions, often one of the tools you're going to use is you're going to replace the squared trig function with its Pythagorean equivalent. This is where knowing those Pythagorean identities really comes in handy. Okay, what else can you do? Well, if you see a lot of different trig functions, one thing you can do is write them all in terms of only sine and cosine. Every single trig function can be written as just sine or cosine. Now, what happens if you've got fractions that have multiple terms in the numerator? Well, if you see that going on, one thing you can do is separate your fractions into multiple fractions. So if you have something that looks like this, a plus b is divided by c, we can break it up into a over c plus b over c, and then treat each of these separately. What else can we do? Well, we can look at trig functions that are really complicated or quadratic as things that might be able to be factored. We could look for a GCF, or maybe it's written as a difference of squares and we could factor it using that pattern. Another clue to look for, what if you see lots of fractions present? well, why don't you try combining them into one fraction and make sure that they have common denominators? You may end up with an expression that looks familiar in the numerator and or the denominator that you can then simplify further. And last, what if your expression includes two of the three components of a Pythagorean identity, but they're not squared like in the Pythagorean identities? Well, in that case, you may want to consider using a conjugate. And using a conjugate to rewrite that expression would allow it to become a Pythagorean identity, and then you could replace it with its equivalent. Okay, so those are a lot of the tools that we're going to use. What are some other things you want to keep in mind? Well, one of the things that you want to keep in mind is going back to that idea that there's more than one way to verify. Often it's easiest for us to only work with one side of the equation. When we do that, we really kind of know where we're supposed to end up. We're supposed to end up with the one side looking like the other. And so while that's possible, sometimes it's not always possible. What you want to do is focus on the more complicated side of the equation and then manipulate it so that it ends up looking like the simpler side. Another thing that you want to keep in mind, don't be afraid to start over. Sometimes you may reach a dead end and go, this is not where I wanted to go with this at all. You might want to go back and start over and try a different route. That's okay. The last thing, you've got to start somewhere. You've got to try something in order to solve the mystery. You can't just stare at it and hope it's going to solve itself. All right, so we've really talked about some of the tools to use when solving mysteries of verifying identities. In the next video, we're going to run through some examples that actually use these tools, and I will see you there.